We often think of Earth as just this static background to our daily lives, right? Like it's just a giant silent stage where human history plays out. But in this explainer, we're going to dive into the data to show you that Earth is actually an incredibly dynamic, deeply interconnected system. It's a place where rock, air, water, and life are in a constant, fascinating conversation.
The ground is not silent. It preserves memory. I absolutely love that quote. Every single time you walk past a sheer cliff face or, say, a carved riverbed, you are literally looking at the geological memory of the planet. It's wild to think about, but a simple limestone outcrop you drive past on your way to work might have been quietly recording the chemical makeup of a vanished tropical ocean for 300 million years. The physical evidence beneath our feet holds the ultimate clues to our planet's ancient worlds.
So, here's our roadmap for this explainer. First, we'll look at memory written in stone. Then we'll dive into the atmospheric engine, explore the global water cycle, examine weather hazards in Japan, and finally, wrap up with our changing climate.
Let's jump into Section 1, Memory Written in Stone. Okay, so when materials like sand, mud, or even volcanic ash settle down, they form these distinct layers we call strata. But the true insight here isn't just that stuff settles, it's how sheer pressure and deep time transform soft ocean mud into an unbreakable historical record. These strata act exactly like pages in an ancient, maybe slightly torn manuscript. Just a single band of sandstone can tell the story of a vast, arid desert, while the layer right next to it, packed with microscopic shells, speaks of a warm, shallow sea. It's like a giant puzzle.
To actually read these rock pages, scientists rely on two fundamental clocks: relative age and absolute age. Relative age establishes the chronological order. Basically, assuming the layers haven't been violently disturbed by something like an earthquake, the lower layers are older and the upper layers are younger. Makes sense, right? But to pinpoint an exact number of years, researchers turn to absolute age, which measures the steady decay of radioactive isotopes within the rock itself. Merging these two methods allows us to piece together a remarkably precise timeline of Earth's history.
And what a history it is. Our planet is roughly 4.6 billion years old, and we divide that into massive eras like the Paleozoic, the Mesozoic, and the Cenozoic. To truly grasp the staggering scale of this deep time, consider this. If Earth's entire 4.6 billion year history were compressed into a single 24-hour day, modern human existence would take up less than the very last second before midnight. We are just the thinnest, most recent sliver on the very top of this timeline.
Moving right along to Section 2, the atmospheric engine.
Now, if we look up from the rocks, our air is vastly composed of nitrogen and oxygen. But the true drivers of our climate, they actually hide in that remaining 1%. Trace gases, particularly water vapor and carbon dioxide, act as the invisible engine for our entire climate system. Water vapor provides the latent energy that drives massive storm systems, while carbon dioxide basically governs the Earth's thermal baseline through the greenhouse effect.
Solar heating ultimately dictates this atmospheric engine, and it creates this relentless push and pull of air masses across the globe. It's an ongoing thermodynamic battle between high-pressure systems, where sinking, warming air gives us those nice clear skies, and low-pressure systems, where rising, expanding air cools to generate intense precipitation and storms.
When these pressure dynamics scale up over massive stretches of warm ocean, you get a typhoon. It's essentially a gigantic, self-sustaining heat engine. As moisture rises and condenses, it releases latent heat. That heat then fuels even more updrafts, which drops the central pressure even further. And all the while, the Earth's rotation whips the entire system into a highly organized spinning storm. It is an absolutely stunning, albeit volatile, demonstration of Earth's interconnected physics.
Which brings us to Section 3, the global water cycle.
As we just saw with typhoons, the ocean serves as the ultimate fuel tank for the atmosphere. Because water absorbs and releases heat way more slowly than land does, the global ocean acts as a massive thermal regulator for the entire planet. Through constant evaporation, it supplies the immense volumes of water vapor that power atmospheric circulation. So, the ocean isn't just a geographical basin, it is the beating heart of the global weather system.
We all know the basic mechanics of evaporation and rainfall, right? But the absolute key takeaway here is continuity. A highly localized rainstorm over your neighborhood isn't some isolated event. It's just one visible fraction of a massive, continuous global conveyor belt of water. This cycle relentlessly connects the deepest ocean trenches to underground freshwater aquifers and right to the municipal water systems of our modern cities. It's all connected.
Let's zoom in a bit for Section 4, Weather Hazards in Japan. Japan serves as an exceptional case study in how these planetary systems manifest locally. The archipelago's unique topography means it catches the extreme ends of multiple global engines. You have the collision of the Asian continent and the vast Pacific Ocean, generating massive winter monsoonal snowfall on the western coast, literally dumping meters of snow in just a few days. But then, it simultaneously sets the stage for staggering urban heat waves in eastern megacities during the summer.
There is a critical distinction we need to make here. Extreme weather, that's a natural event, but it only becomes a disaster when it intersects with human infrastructure. In Japan, the real danger emerges when unprecedented rainfall hits heavily populated steep mountain slopes, triggering rapid debris flows. Or, think about what happens when sudden downpours completely overwhelm the drainage capacities of paved urban centers. It leads to instant, incredibly dangerous flooding. And that leads us to our final section, Part 5, our changing climate. When analyzing these global systems, the distinction between short-term weather and long-term climate is absolutely crucial. Rather than just focusing on a single storm or an unusually cold winter week, the data indicates we really need to view climate as a pair of weighted dice. As the climate changes, those dice are progressively loaded. This subtly alters the underlying probabilities and ultimately dictates the long-term patterns of the extreme weather events we experience.
The sources point out that Earth's climate is fundamentally dictated by a delicate energy balance between incoming solar radiation and outgoing infrared heat. Naturally occurring greenhouse gases trap a portion of this outgoing energy to keep us warm. However, the data highlights that human industrial activity has introduced a rapid influx of these greenhouse gases into the atmosphere. This artificially traps significantly more heat and is rapidly altering our baseline planetary energy balance. So what does this all mean for us? Because of this altered thermal baseline, the hazards we discussed earlier are directly amplified. Basic atmospheric physics tells us that warmer air can hold significantly more water vapor, which unfortunately turns routine seasonal storms into severe flooding events. Concurrently, warmer oceans act as higher-octane fuel for much more intense typhoons. And as thermal expansion and melting ice raise our sea levels, coastal storm surges naturally become far more destructive. We started this explainer by looking at ancient strata, the memory of Earth meticulously written in stone. Well, we are currently living in a radically new geological moment, one where human activity is fundamentally altering the atmospheric engine and the global oceans. So, thousands or even millions of years from now, when the Earth inevitably turns our present world into just another compressed layer of rock, what kind of layer will our own age leave behind?